In this video, we're going to use a flowchart to determine if molecules are polar or non-polar overall. So let's go ahead and start off with a few examples, such as let's do NH3. So for NH3, what I'm going to do is I'm going to draw its Lewis structure first. And then I'm going to draw out its Vesper shape. So you get practice doing all these different skills in one question. And the Vesper shape can be obtained from the Vesper chart in your toolkit. And what we have to do is we have to calculate the bonds, the bond polarity. And really there's only one type of bond, the NH bond. So we'll go calculate the bond polarity between N and H. So our delta En is equal to, let's go find the values, 3 minus 2.1. Which is 0.9. And that ends up being a polar bond. So the bonds are all polar. We know that. Now let's go take a look at our molecule symmetrical using a flowchart. We start by asking ourselves the questions: are there any polar bonds? Yes or no. We're not going to be in the no area. We're going to be somewhere around here. Next, we ask ourselves, are there lone pairs around the central atom? And our answer to that is yes. So we have polar bonds. There's lone pairs around the central atom. Therefore, that makes our molecule symmetrical. For the most part, providing that you're not dealing with an exception, and we'll see some examples of that later on, when you have polar bonds and you have lone pairs on your central atom, that generally makes you a polar molecule. So what that means is if we draw our dipole vectors, they're pointing towards nitrogen because nitrogen is more electronegative, and they're not going to cancel out. Overall, this molecule is not considered symmetrical. The dipoles do not cancel out, and therefore the molecule is polar. Let's try another example. So we'll do CF4. So let's draw the molecule CF4 as a Lewis structure. Then we'll draw it as a Vesper shape. It's tetrahedral shape with 2 of the fluorines in the plane, and then 1 with our wedge here coming out at us, and then 1 with our dashed line going away from us. So we need to calculate the bond between C and F. This is a delta En is 4.0 minus 2.5, which is 1.5. So those are polar bonds. So we are dealing with polar bonds again. Let's go to our flow chart. We have basically the question, are there polar bonds? We're not the no region, we're at the yes region. Are there any lone pairs around their central atom? And that's going to be a no. So the next question is, are the atoms the same? And it looks like the atoms are the same. Around the central atom, they're all fluorines, so yes. And since they're the same, that means our molecule overall is symmetrical. That even though there are dipoles, even though we're drawing these dipoles out like this towards the fluorines, that they will be canceling out because they're pulling in directions with equal strength that are symmetrical, that make a symmetrical arrangement to cancel them out. So therefore we have a non-polar molecule in this case. Non-polar molecule. If the atoms were different, let's say there was an H somewhere instead of an F, then you'd probably have polar because now it's no longer symmetrical. You're not pulling in equal directions anymore. So that's why if we chose the no, we would have been an asymmetrical or polar molecule overall. So that's how we could use our flow chart here to help us figure out if our molecule is symmetrical or asymmetrical, and therefore polar. So let's try out the molecule pH3. So if we draw out pH3, you get something like this. And if you want to draw out its 3D structure, you get this. And we need to calculate the electronegativity difference to figure out the bond polarity here. So the delta En is equal to 2.1 minus 2.1. 2.1 minus 2.1, which is 0. Now, it's probably not exactly 0. The electronegativity values aren't exactly the same. We only have one decimal place. If we had a few more decimal places, we'd see there'd be a slight difference between them. But either way, right now, we can say that these are non-polar bonds. So the bonds are non-polar. Now let's go take a look at what that means. Does that necessarily mean our molecule is non-polar? Well, here's our question. Are there any polar bonds? It's not yes. We're at the no region. Are there lone pairs? We're at the yes region. There are lone pairs in the central atom. So if there were no lone pairs, like in CH4, for example, then we could say our molecule is symmetrical and the electron density distribution is roughly the same throughout. However, there are lone pairs here. And because there are lone pairs, that is going to make our molecule asymmetrical overall. So even though there's no polar bonds, our molecule is still nonpolar because of this lone pair over here, making the molecule asymmetrical and leading to an asymmetrical spread of the electrons overall. So you could actually have a nonpolar, you could have a molecule with only nonpolar bonds that's considered, I shouldn't say nonpolar, that's considered polar is what I want to write, because of the asymmetry caused by the lone pairs. So we don't have polar bonds, but there are lone pairs in the central atom, so it makes our molecule polar overall. So those are some practice problems related to determining if a molecule is symmetrical or asymmetrical. If it's symmetrical, dipoles cancel out and you're nonpolar. If it's asymmetrical, dipoles do not cancel out and you're considered polar. A great way to understand this concept is by taking a look at the visuals that we have listed for us over here. So let's go take a look at them. This shows you the polarity of various shapes. So if we look over here, we have a linear molecule. And let's assume that we have polar bonds pulling in this direction, this direction. If we look here, they'd pull in equal and opposite directions, and so we'd predict that to be nonpolar. Whereas if we have a linear molecule, but we have a different atom here compared to this one, and one was pulling with more direction to one side compared to the other, well, this would be considered polar because they're not canceling out anymore. If we take a look here, let's see if we can predict which one's polar and which ones are nonpolar. So if we look here, they're pulling in with equal forces since it's the same atoms and there's no lone pairs, with equal forces in a symmetrical way, and this would make this molecule nonpolar overall. Yes, here we do have three atoms in a similar arrangement to here, but one of the atoms is different. So it's possible that these two are pulling with greater force compared to this one, and as a result, that's leading to a polar molecule. Here we have two atoms pulling, or they might be going in this direction here, doesn't really matter. But the point is that this molecule is no longer symmetrical because of the lone pair here, so this would be considered polar. If we take a look here, we have a tetrahedral arrangement with all the same atoms, and here we have a tetrahedral arrangement with different atoms. The one with the same atoms, they'd likely all cancel each other out because of the equal force of pull. Here, since it's an unequal pull, we'd likely have polar. And then same thing with these lone pairs here. So these are tetrahedral arrangements in terms of electron arrangements because you have 4 electron groups. And basically the only one out of them that's nonpolar is going to be your pure tetrahedral with the um, with the equal atoms on or same atoms connected to the central atom. Um, Here, as you can see, we will cancel out going up and down here. And then over here, it's almost like a trigonal planar on the equator here. Those will cancel out as well. And so that leads us to a nonpolar molecule. Now, if we take a look here, be careful. I said if there's lone pairs in a central atom, it makes your molecule polar. However, you'll notice that these lone pairs cause the molecule to be linear, almost like a carbon dioxide molecule, and so they'll pull with equal strength to both sides, leading your molecule to be nonpolar overall. So this was an example of an exception. We have an AX2E3. If you see an AX2E3, even though there's lone pairs on it, it's going to be nonpolar overall because it's now linear and they'll pull in opposite directions. It's symmetrical. If we take a look here, you'll notice that the different atoms, you have different atoms on here, so this is likely polar. Here you have the lone pair, so we're dealing with polar. And here, these two may cancel out, but at the end, this is still present, so that's considered polar. We can take a look at the octahedral arrangement. Up and down cancel out here. These cancel out this way. These cancel out this way. So we're dealing with nonpolar. Now, take a look at this scenario here. These would cancel out this way, and that way. These would cancel out this way and this way. So even though there's lone pairs in this situation, this is one of those exceptions where even though you have lone pairs, you're nonpolar. So this is the second exception where you have an AX4, 1, 2, 3, 4, E2. Here, as you can see, these would cancel out, this would cancel out, but this would not because they're different atoms, so nonpolar. Here, this would cancel out, this would cancel out, but this is missing an atom on the other side to cancel it out. So that would be polar as well. And so you can go through a variety of practice problems using the flow chart and using the 3D depictions that we saw throughout this presentation. You can try out molecules like CH4 and the answer keys are provided. ICl3 again, all provided. As you go through it, determine what the shape is and determine if it's polar or nonpolar using the chart provided there. So go through the examples, make sure you get the right answer, make sure you can use this chart well, make sure you know what the general exceptions are for when lone pairs lead to nonpolar molecules as well, and you should be on the right path to being able to classify molecules as polar or nonpolar, which will lead us to a greater understanding for the different types of physical properties that substances might have based on polarity. This one's a bit of a challenge. The only hint I'll give you is that this molecule is different from this molecule here, even though they look the same. And I would recommend you draw in your dipole arrows where they belong, and you'll be able to determine if you're dealing with a polar or nonpolar molecule. So these are a little bit of a challenge. You have a double bond here, which means this molecule stays the way it is. It's not going to rotate with the Cl going up. And this molecule here is going to stay the way it is. It's not going to rotate with the Cl going back down. So basically draw on your dipole vectors, and you should be able to figure out if you're dealing with a polar or nonpolar molecule in this situation. And you should be able to answer questions like this. So is this polar or nonpolar, and explain why? Is this polar or nonpolar, and explain why? And then before all these problems and all these visuals here, there were a few additional practice problems that you could try out. Here, for example, explain why one is nonpolar and the other is polar. Can you provide the proper terminology? So in this video, we went over some examples of polar molecules and nonpolar molecules identification. A few quick tips to remember. If you see things like F2, O2, Cl2, I2, Br2, these are all considered nonpolar because they're perfectly symmetrical. They cancel out. It's like having this molecule here It's a completely pure equal share, and it's perfectly symmetrical down the middle, with electron just essentially being shared right down the middle equally because it's two of the same elements. So you wouldn't even have to draw this in. So when you see these diatomic molecules like this, or N2, for example, you know you're dealing with non-polar molecules. It's a pretty quick guess, especially if you have multiple choice. Diatomic molecules, non-polar, because it's an equal pull by the same element bonded to itself. So remember little tips and tricks like that, and that should help you to get through a lot of the problem solving more effectively and efficiently.